geometry. Today we'll be doing some similar triangles and the Pythagoras theorem. And before we get started, if you want to get a calculator out, because we'll be like using the calculator to do some square roots for Pythagoras today. Cool. Okay, so we'll start off with similar triangles. They're essentially like pairs of triangles that are like, they've got the same angles, so they kind of look the same, except one might be like larger than another. So it's like, so we might have these two. Whoops. Yeah, it's not very well drawn, but you can kind of see how they have the same angles, except their sides are quite different. So these would be similar, like these angles are all the same. It's not a very good drawing, but you get the idea. Okay. Okay, here's a bit of a definition kind of thing. So we can have these two triangles, ABC and XYZ. And you can see how angle A and angle X are the same, right? And angle C and angle Z are the same. Angle B and angle Y are also the same. So this means that these two triangles are similar. However, their side lengths are not the same, but we actually can find this ratio between their side lengths. So if we have, for example, the side AB, and just get my pen out. Yeah. So we have the side AB and XY. They're kind of like equivalent to each other. You can see how they're in the same position. So these two, the ratio between AB and XY is the same as the other equivalent sides. So we have BC and YZ. So their ratio is the same. Like, you know how the line is like, it means dividing, right? So AB over XY is the same as BC over YZ. And this is a bit of notation. If you want to say that they're similar, you can kind of do that. Right. All right, so here are some examples. So sometimes similar triangles, when you see them, they're not like perfectly lined up to each other. So there might be like one of them is like right side up, the other's kind of like upside down. So you have to rotate it so that it matches, so that the angles will match up. So over here, what I've done to the right, the triangle on the right, PQR, is that I've flipped it upside down and I've also like rotated it. Wait, no, I've flipped it upside down and then I've flipped it left to right as well. So took a bit of tech skills to do that. But yeah, I ended up with this one right here. So now we can see that they're equal angles, the yellow angles, double angle line thing. They're all in the same position. So that is good for us because now we can like really easily tell which sides are equivalent to each other. So we've got JL, QR, they're like equivalent to each other, and for the other pairs as well. And this is telling us that the ratio of JL, QR equals ratio K PQ and LK and RP. So we have here, this one actually has some numbers for us. So we know that LK is 16, right? So I'll just replace that with a 16. And I'll replace RP with 20 because we can see it in the diagram. That is 20. So we kind of have this fraction here, 16/20. To make it easier, we could like simplify it to 4/5 or something. So we know that the ratio of LK over RP is 4/5. So we can actually use this to work out some other sides. So for example, we have JL is 24. And we want to find out what the bottom is. Now we know that this must be equal to 4/5. So we can use equivalent fractions to work out what the bottom is. So does anyone want to have a go at telling me what the bottom would be? This will be the length of QR. Feel free to type your answers in the chat or like annotate the screen. Any ideas? It's just equivalent fractions. So, whoops, just annotate it. So to get from 4 to 24, we had to multiply by 6, right? So when we do equivalent fractions, we want to do the same thing to the top and to the bottom. So to the bottom, we would do the same. So what would that get us if we multiply by 6? I just see someone's typed in the chat, 30. Yeah, nice. Cool, so 30, that tells us that QR, this one over here, is 30, and don't forget our unit, meters. Okay, now we can also see that PQ is 25. And so we know that this fraction must be equal to 4/5, right? So anyone want to have a go at working out what KJ would be? So this one here. Yeah, 20. Good job. Just come into the chat. All right, so 20. So we know that this is 20 meters long. And yeah, that's how we use similar triangles to help us work out side lengths. All right. Oops. Okay. And here's just another example. So the way that they did this question was a little bit different from the way I just showed you. So I did equivalent fractions, right? But they did it like a little bit more algebraically, I guess. But it's the same result. So they had these two ratios. They got it because they have YZ. Oh, I shouldn't use purple. It's not very visible. Okay, they have YZ and BC. So YZ they represented with the letter X, and then BC with the, they plugged it in. They substituted 8 into there. And then they have the equivalent sides XY here and AB over here. So we know that XY is 32, so we can just sub that in, as well as AB is 20. And we could use equivalent fractions and just say, well, you know that 12.8 should go on the top. But then this is a bit difficult because it's kind of like a decimal and you can't really work it out straight away. So what they did was the more algebraic way of multiplying both sides by 8. So if you multiply the side by 8, that kind of gets rid of it from the bottom and then moves it up to here, times 8. And yeah, that's how they got this part, 12.8. Cool. So this is just a bit of a summary of the ways that you can tell that two triangles are similar. So we know that if they have all the same angles, then they're similar. So for example, you have two triangles. Their angles might be 50 degrees, 60 degrees, and 70 degrees. And if you see another triangle and its angles are also 50, 60, 70, then you know that these two triangles must be similar. And another way is that if they give you the side lengths of the triangles, and then you can work out the ratios between the equivalent sides. And then if the ratios are all equal to each other, then that means the two triangles are similar. So here, we see that angle A equals angle X, angle B equals angle Y, angle C equals angle Z. So that tells us the angles are all the same. And so they must be similar. Also the ratio. Well, here they didn't give you the numbers, so you couldn't have worked it out from this. But if they gave you the numbers, then you could have worked out that the ratios were all the same. Okay, here's some practice questions. Yeah, guys, feel free to annotate or send your answers through in the chat. So for this one, just maybe circle the two triangles that are similar. Right, I'll start you guys off. So we have this one over here. So, oh, someone circled it. Yeah, good job, Emmy. So we've got 130. So we can't really tell straight away, right? So I'm sure as Emmy has done, she would have worked out what the angles all are, because the angles in a triangle add up to 180, right? So we've got 130 and 50, and ta-da. Yeah, nice job, Khadija. So we've got these two triangles. So this must be 35. And this is 55 and 90. And we know that once again because angles in a triangle add up to 180. Okay, the next question is, someone's already having a go. 4, 5, 6, and 6, 10, 8. Not quite. So let's have a think about the ratios of the sides. So we can kind of simplify it if that makes it easier for you guys. So if we kind of divide everything through, we can still kind of get the ratios. All right, so we've got, first of all, this side, and it's a 6, right? So what would be the equivalent side on this triangle? Well, we can tell from the angles that this side kind of is surrounded by these two marked angles. So it'd be 6 here, 9 here. All right, and all right, here we've got this side and this side, 8 and 12. And 10, and 15. And if we work out the ratios, so we've got 6 ninths, and we've got 8 twelfths, and 10 fifteenths. So do you guys think that these two triangles are similar? Because if we've got all these ratios, are they equal to each other? Sorry guys, my computer's just having a moment. There we go. Okay, so what we had was that these two triangles were similar because we had 6 ninths, 8 twelfths, and 10 fifteenths. And this is all equal to 2/3 if you simplify it down, right? So they're all equal. So that means that these two are similar. Right, for the last one, it's a little bit trickier, but I'll give you a clue. So if we have 6, 11, 6 and 11, yeah. So we can kind of know that straight away they aren't similar, because if they have two of the same like side lengths, but then the angle in between is different, then like it's kind of like if you've got two of these like pens and then you like open them up differently, then obviously the other side is going to change, right? Even though these two sides are the same. So like that. So if the other side is different, then this side to this side, the ratio was 1, 6 over 6, right? And then 11 to, yeah, good job, Amy. And then 11 over 11 is 1, but then the other side can't be the same. So, however, if we look at this one, we can work out that, so I've got our 25 degrees here. I'll just use a brighter color. So I've got this side and this side are equivalent. So if you use your calculator maybe, or do some quick mental maths, you'll get that the ratio is 1.7, right? You've got 10.2. Over 6 and 18.7. And also, just because two sides have the same ratio doesn't mean that they're similar. So, but because they have this same angle also, then it tells us that they're similar. This is kind of a bit different from what I'm teaching you guys today, but there is this thing for similarity called the side angle side thing. You might want to look it up. I don't think I'll have enough time to like go through that today, but yeah, it's quite cool. Whoops. All right, have a go at this question. And remember that these two triangles, they're not aligned, right? The angles are kind of like, they're not in the same position for the two triangles. So just have a think about that before you decide which sides are equivalent. So maybe you guys want to start off by like color coding, maybe marking the equivalent sides with the same color. If anyone would like to annotate that. I think someone asked me, what does angle with two lines mean? Sorry, when did I say that? I was wondering what you mean by angle with two lines. Anyone want to have a go? Oh, yes. Let's see, 24. All right, do you want to write your working up maybe, Emily? I think that's right from what I remember. I'll just have a check. Yep, that is absolutely correct. Maybe you want to just write down how you got it, maybe the ratios that you used. Nice, yeah. Yeah, so what Emmy is doing is she divided the ratios and she got an answer. So that is a good way to go about it too. So I showed you like equivalent fractions and the sort of algebraic way, but Emmy's way is also perfectly fine too. So, good job. Nice. All right, for the other one, we've got 32 over here, and it's equivalent to Q. Now this triangle seems to be like 1.2 times the size of the other one, right? So if we go through and do 32 divided by 1.2, we're going to get 26.67 if I round it to 2 decimal places, or you could just say 26 and 2/3 of a meter. All right. Oops. Oh no, didn't get rid of the annotations. Okay, here's just another bit of a challenge example. So here we can see that we've got two pairs of similar, sorry, not two pairs, a pair of similar triangles. So we've got triangle XYZ, which is this one right over here. And we've got a bigger triangle, AZB, like that. And we know that they're similar because they both like share this angle, right? And this angle of XYZ is equal to this angle in the bigger triangle. And we know that because they've marked out these parallel lines for us, right? So we can use corresponding angles to work out that they're the same. And we've got another pair of angles here. They're also corresponding, so they're equal. So that's how we know that they're similar. Now the smaller triangle, we've got the side lengths are 11, 14, and Z. And then the bigger one, it's like this whole length right here, right? And we know that this part is 11, and then the other part is X. So if we add it up, we get 11 plus x centimeters. And similarly for the other side, it's 14 and 8. So we get 22 and then 12. All right, and now we can use some algebra. Because we want to figure out what x is, we kind of have to like put it into the equation. So we've got the side AZ and XZ. It's getting a bit messy. I'll just rub out some stuff. Okay, so we've got the side AZ and XZ. So XZ is this one here. And they're equivalent to each other, so we put them in a ratio with each other. And then BZ and YZ, the smaller one, they're equivalent. So we say that these two ratios are equal. Then we just plug it in. So we know that AZ is the 11 plus X side. And then we've got it over 11, which is XZ. Same for the other side, 22 over 14. And then we can use some algebra. So they skipped a few steps here, but what they did was they'd multiplied, because they have 11 and 14 on the bottom, right? And when we solve these equations, we don't really like having numbers on the bottom as fractions. So fractions are like dividing, right? So if we multiply by the bottom number times 11 times 11, because we do the same thing to both sides. And then on the other side, we want to get rid of times 14. Sorry, we want to get rid of divide 14, so we times it. So we end up multiplying by 11 and multiplying by 14 on both sides. So on this side, we multiplied by 11 and we got rid of the bottom, but we've still got to multiply by 14. So if we multiply the top by 14, this is what we get. And then on this side, we were dividing by 14. So we multiplied by 14 and that canceled out, but we've still got to multiply by 11. So 22 times 11 gets us 242. And then you subtract 142 from both, 154 from both sides. And divide by 14 on both sides. And it gives you x is 6.3. So that was a bit of algebra involved, a bit challenging. All right. Now, for this one, you have to identify which of the, well, there's only two triangles, so you know that they must be similar, but you have to kind of prove why they're similar. I've just had someone ask me in the chat, and yes, we are doing a block it today. But I feel like we might go slightly over time. So if you guys are down for it, we can do block it, but it might go a little bit past 8 o'clock. And we'll be doing two today. We'll be doing one for similar triangles and one for Pythagoras. All right, I might just get us started on this question. So we have these two angles and they're vertically opposite to each other. So this tells us that they're equal. Okay, and we have these two. They're alternate angles, right? We've got these parallel lines. They're on different sides of the transversal. So they are alternate. That means that they're equal. And we've also got these two. And then we can just work our ratio magic and see that W, this side, is equivalent to this side over here. So we've got our ratio W over 49 equals, and we've already been given a pair of equivalent sides, so we can work out the ratio of 35 and 20. We've got 20, 35. And if you were to do some quick maths, you would come out with, so this side is 4/7, right? So this would be 28, I believe. And then if you do the same with t, so 30 over t. And remember when you're doing these ratios to be consistent about which sides you're putting on the top. So for my one, on the top, I've got always the smaller triangle on the top of the fraction. So W is from the smaller triangle, so it goes on the top. And then 49 is from the other triangle, so it goes on the bottom. And here I've got 30, which is from the smaller triangle, and T from the big one. So 30 on top, T on the bottom, equals 4/7. And what did we come out with for T? I'm gonna check. Okay, that should have been 52.5. Anyways, I think we'll move on to Pythagoras now, because okay. Oh yeah, this one is just an extra practice problem if you want to do that in your own time. This one you will have to draw your own triangles because they didn't provide them for you, right? So you'll kind of have to draw a diagram that goes like this. Whoopsies. Yeah, that's just to start you off, but I'll leave you to do that in your own time if you wish. Okay. Right, so now we'll move on to Pythagoras. And I was wondering how many of you have already done it in school. So if you have, maybe like give a thumbs up or something, just so I know how much time to spend on this part. Oh yeah, a couple of you. All right, so this is the Pythagoras theorem. It's named after this old like Greek dude from a couple thousand years ago. He was called Pythagoras. I'm not sure if he actually came up with it, but anyways, this theorem is named after him. And it says that if you have a right angle triangle, and it only works for right angle triangles, so just be a bit careful with that. If you've got a right angle triangle and you take the hypotenuse is this longest side, it's like the slanted side, and you square it, then so let's just annotate it. So we've got C is the longest side. So I've got, if you square it, it's equal to the other two sides, like squared and added together. So for example, you might have the hypotenuse is 5, this side is 4, this side is 3. So if you work that out, 5 squared is 25, and it's equal to 3 squared, which is 9, plus 4 squared, which is 16. So both sides are equal to 25, right? So that's an example of how it works for a right angled triangle. So here's another example. We've got a hypotenuse here, and this time we're going to use the Pythagorean theorem to help us work out what it is. So we know that the other two sides, if you square them and you add them together, you're going to get the square of the hypotenuse. So we did 5 squared plus 12 squared, and that got us 169. So we know that C squared, or the hypotenuse squared, must equal 169. So if we take the square root of that, we're going to get what C is, what the hypotenuse is. And that gave us 13. Oh, I love this little joke over here. find x, they just circled it. Yeah, I wish I could do that on my maths tests. But here's a bit of a tip for finding side lengths. So we've just looked at how to find the hypotenuse, right? So we square both of the other sides, we add them together, and that gives us the hypotenuse squared. And then we square root that to get the hypotenuse. However, if you have, if they give you the length of the hypotenuse and another side, then you'll have to do subtraction. And I'll show you an example of that now. All right, so here we have this triangle here on the left side. So we know that the longest side, the slanted side, the side that's opposite the right angle is always the longest side. So the right angle is here, right? So we've got 30, we've got 18, and we want to find what A is. Now, if we use the A squared plus B squared equals C squared, so A and B are just the other two sides. C squared. So we want to find A, right? So we know that A squared equals C squared minus B squared. So it's just showing that if you want to find another side, you have to do subtraction rather than addition, which is what you did for finding the hypotenuse. So here we got A squared is 30 squared minus 18 squared, blah, 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 same process. And then that gave us 24. And this question requires us to find X as well. So now that we've found 24, we've got two of the sides of the triangle on the right side, and we want to find the hypotenuse. So once again, we can add the squares of the two sides, and then we take the square root of that to find X. Okay. Just skipping back. So here you guys might want to get your calculators out and yeah, just try to figure out the length of H and T. And I'll work the answer out while you do it too. I think you might want to have a check of your answer there. Oh, guys, if you don't have a calculator, maybe you want to, if you're using a device, you can probably Google like online calculator or something. And that should come up. As long as it has a square root thing, then you can do that. Yeah, nice, Amy. And what does the square root of that number come out to be? Yeah, good job, Trinity, 7.02. And we always want to add our little unit, which is meters, so that's really good. Nice. Okay, the square root of this ginormous number right here would be 83.18. I'll just round it to, and millimeters. So for geometry, it's quite important to always put the correct unit. I remember in one test that I did, I think I wrote centimeters instead of meters, and then that cost me like half my marks, which is kind of sad. Yeah, that's why I've always remembered to use the correct units since. Okay. Oh wait, no, that's the one we've already gone through. Here's a video about proofs for the Pythagorean theorem. Do you guys want to watch that now, or do you want to do it afterwards in your own time? Up to you. Maybe thumbs up if you want to watch it now. I think most people are saying in their own time. So I'll just move ahead from here onto the next part. Okay, so the Pythagorean theorem is quite useful in real life as well, especially like for questions where you want to find the shortest distance. So for example, like, I don't know, you might have a table or something. Okay, that's a bad example. You might have a field and it might be like, I'll just use these numbers. So you might have a field, and you're this beautiful blob over here, and your friend is this other beautiful blob over here. Okay, and you want to find the shortest distance to get to your friend. Now the field, as you know, is 49 and 23. And I'll just say meters, 23 by 49 meters. So if you go there in a straight line, then that is going to be the shortest distance that you need to get to her. Because you don't want to like go around the edges like that. That's going to be like 72 meters altogether. And that is too much walking. So if we use Pythagoras to help us figure it out, then we can do square root of 49 squared. I'm kind of just combining two steps into one, but I added the squares of the two other sides, and then I square rooted it. And that will come out to be 54.13 meters. And look, you just saved yourself quite a bit of walking compared to like 72 meters if you went like that. So yeah, that's kind of how you can use it in real life. In this question as well, they have like a rescue helicopter and it wants to fly directly in a straight line to a snowfield. And yeah, we could use that to figure out how long it needs to fly. All right. And here's a few practice questions for you guys. We'll just do like maybe 3 of these questions, then we can do some blockets. Yeah. And when you're doing these questions, it's useful to like put a little square where the right angle is. Here we know that it's a right angle because you have a wall, and obviously the wall is like perpendicular to the ground. They're at 90 degrees to each other. So we can use Pythagoras. Yeah, so it is 2.7 meters. And I think someone wrote 8 meters. So you might have done, you might have added the 2 squares together and then you took the square root. So here we're actually finding the shorter side, right? Because we already know the hypotenuse is 6.4. So if you want to find the shorter side, one of these sides, then you would do subtraction. Yeah, it is quite easy to get confused, but yeah. So good job to 2.7 meters. That is good. And the way we got that would have been a squared equals c squared minus b squared equals, so c squared is the hypotenuse, right? So we do the, oops, hypotenuse squared minus the other side, other shorter side that we know. And then a would be the square root because the square is that, so the square root of this would be a. Yeah, and that would have given us 2.7. Okay, next one. This one, it doesn't give you the right angle triangle like side length straight away. You might need to do some working out of that yourself. So just gonna give you guys a clue. So we already know that this side is 1,250, this side right here. However, the bottom side, we're not given it straight away. I see someone's 3,361. I'm not quite sure what you've worked out there. Sorry. 3,361. Let me see. Alrighty, so we know that this side is 1,250 millimeters. And then we know that the total length of the bottom is 6,240 millimeters, right? But for this triangle, we're actually only looking at half of that side. So I think this is quite close. I think it comes out to be quite close. All right. I'd like you guys to work out this bottom side first. So we know that altogether it's 6,240 millimeters for the whole bottom, right? But then for this triangle, it's only half of that. Oh, I see someone writing. Yeah, nice fella. So 3,120 millimeters for the bottom side. Because it's only half of the bottom, right? Okay, now that we know the two sides of the triangle, we can have a crack at figuring out what t is. Yeah, nice. 336. Oh, sorry. This one was actually right all along. I think I read it wrong or something. Yeah, sorry guys. That one was good. Yep, so we would have worked out the two sides, then we would have added their squares, and then we would have taken the square root of that. So yeah, sorry guys. All right, let's move on to the next one. Oops, I'll just clear the annotations. It's a bit crowded on the screen. Right, so we only have one triangle in this diagram, so it's kind of obvious that if we want to use Pythagoras, it's got to be a right angle triangle, right? But can anyone tell me what the reason this triangle is a right triangle would be? So how can we prove that it is a right triangle? So we can actually use the Pythagoras theorem here. Yeah, the tangent rule. Yep, exactly. So it's the tangent rule is that the radius must be perpendicular to the tangent, right? So this is from like, I think last week maybe, or last week, where we've got the circle rules and we have a radius touching a tangent at one point, and here they must meet at 90 degrees. So yeah, nice job, guys. And we can use Pythagoras now that we have proven that it is a right angle triangle. Oh, I see someone's written 14.3 on there. I'll just have a little peek at the answers. Let's see. Why don't we start off by labeling some of these sides? So we know that a point T is exactly 7 millimeters from a circle, and line TA is a tangent to the circle, blah, blah, blah. Okay, TA is 12.5. Whoops. So we know that TA, this side, is 12.5. We've been given that. And we know that side over here, so this part is 7, and it's because the point T is like 7 centimeters from the circle, so it means 7 centimeters like outside of the circle. And then we have this part here. Now this part is just the radius, right? So we can label it as R. And this is a bit of a challenging question. So if we use Pythagoras, how do we figure it out? Well, we've got 12.5 squared plus R squared equals, and then this side is R plus 7, right? R plus 7 squared. And this might be a bit tricky if you haven't done quadratics in algebra before, but essentially, if you solve this quadratic, you're gonna get 12. So if you expand that out, yeah, sorry guys, I know this is a geometry class, but once you get to like some of the more complex geometry questions, algebra is gonna be involved. So if you expand that out, this is what you get. And don't worry too much if you're not getting this, because this is just like extension. Equals 12.5 squared plus R squared. And on both sides of the equation, we have got R squared. So we can kind of just get rid of them. Okay, now we've got 14 now. It's 49. Oh, I see Bella's writing something up. Yep, 7 point something is correct. Do you want to just keep going? Yeah, 7.6. Nice. So if you go on to solve this, you've got 14r plus 49. Sorry, can't write. Equals 12.5 squared. And if you solve this linear equation, you're going to end up with 7.66. So nice job. Alrighty. Let's do some booklet now. So I've got 2 lined up today. We'll start off with this similar triangle.